Now we have seen what the strips representation for world states looks like. The internal structure is represented as a set of ground atoms where each atom expresses a relation that must hold between objects in the domain. The next step then is to look at operators with internal structure and actions that are instances of these operators. Remember that actions are what give us the state transitions in our state transition system. For states, I started with some examples and some informal definitions and followed this with the formal definition of what a strips representation state is. For operators, I'll do it the other way around. I will start with the formal definition of what a strips operator is. A planning operator in the strips representation is simply a triple, so it means it consists of three different things: a name, the name of the operator, the preconditions of the operator, and the effects of the operator. The name of the operator, the name that we can use to refer to this operator, is simply given by this syntactic expression. So it consists of a unique name symbol that we can use to refer to this operator. It must be unique to this operator, meaning no other operator can have the same symbol. And it consists of some parameters which characterize the objects that are manipulated by this operator. These objects are defined as variables for an operator, as an operator is generic. They may also be typed if we are using the types extension in PDDL. The components that define the internal structure of an operator are the preconditions and the effects of the operator, and both of these are sets of literals. Remember that a literal is either a positive or a negative atom, so a relation between objects, where the objects are named by the variable given in the operator name, x1 through xk here. The preconditions are simply those literals that we want to be satisfied in the state before we execute an action. The effects are the things that are true after we have executed an action. Again, the effects can be literals, which means they can be positive or negative, and traditionally the positive literals that are effects are often referred to as the add list, as this is something that is asserted in the new state after an action is applied, and the negative literals are referred to as the delete list, as these are removed from the state. An operator is generic in the sense that it only specifies what is manipulated by the operator as variables. An action, on the other hand, is specific because it is a ground instance of a planning operator. So if we take all the variables and choose values, objects in our domain for these variables, then our operator becomes an action. And of course, there can be many actions that are instances of the same operator in our planning domain. Now, here are some examples of operators defined for the DocWorker robot domain. The first example we will look at is the move operator. Move is the symbol that identifies this operator, and the name of the operator is given by all of this expression here, namely the symbol that identifies it plus the three variables that are used to identify its parameters. And these are a robot and two locations: the location we're moving from and the location we're moving to. Then, the internal structure is defined by the preconditions and effects. There are two positive preconditions in this example, namely that the two locations we're moving between must be adjacent, the location we're moving from must be adjacent to the location we're moving to, and the robot R, the robot that we are moving, must be at the location we're starting from. And then we have one negative precondition, and that is given here. This is simply the symbol for negation. That's the not symbol in logic. The negative precondition here says the location M we are moving to must not be occupied by a robot when we move there. So, three preconditions, two positive, one negative. And then we have the effects, again two positive effects and two negative effects here. Let's look at the positive effects first. When we move robot R from location L to location M, as a result, the robot will be at location M, and the location M will be occupied as a result of this action. These are the effects that are added by this operator, hence this is known as the add list. The delete list, or the negative effects of this operator, are that the location L is no longer occupied. We've just moved the robot away from this location. and the robot is no longer at this location L that we've just moved away from. There are a few things that are quite common about this operator, but they are not part of the definition of a strips operator. And those are: all the parameters are actually mentioned in the preconditions. R, L, and M, all of those are mentioned in these three conditions. Also very common is that we have the negative effects of the operator, the delete list, as part of the preconditions, only negated. For the second negative effect, this is explicit here, and for the first one it is implicit. Of course, the location L was occupied before the robot moved away from that, but because we have this precondition, it was not necessary to mention that. Quickly, the two other examples. The second one is that we're loading with crane K at location L. We're loading container C onto robot R. These are the 4 arguments to this operator, and all this is the name of the operator. Again, we have preconditions and effects, and they are divided into positive and negative preconditions and effects. In fact, we have no negative preconditions for this operator. So the positive preconditions are that the crane must belong to that location, it must be at that location. The crane must be holding the container so it can load it onto the robot, which must also be at that location, and must be unloaded so it cannot have a container on it. The effects are that now the crane will be empty after we've loaded the container onto the robot, so it will no longer hold the container, but the container will be loaded onto the robot and the robot will no longer be unloaded. Similarly, there is the put action, which has as parameters a crane, a location, a container, another container, and a pile into which we're putting the container C. The crane must be at that location, and also the pile must be at that location, and of course we want the crane to hold the container. And this precondition here tells us the meaning of this second container D that is a parameter to the put action. Namely, it is the container that is on top of the pile before we execute our action. And the reason why we need to know this is simply such that we can withdraw this from our state. So the container D is, after we've executed the action, no longer on top of the pile, because we have the container C on top of D, and now C is the new top of the pile. So C will also be in our pile, the crane will be empty, and the crane will no longer hold container C. There is also an unload and a take action that reverse the load and the put action, but I won't go through those in detail here. In the previous slide, we have seen some examples of operators of what they look like logically. Now I will introduce the PDDL syntax for defining an operator in a planning domain. This example again starts with a comment introduced by the semicolon that tells us what this action will actually do. And here's the first slightly confusing thing about the PDDL definition. Namely, the operator is called an action in PDDL. So in the strips representation, we consider an action to be an instance of an operator. In PDDL, this is what is called an action. This is actually not uncommon in the planning literature that terminology is not agreed. So you always have to make sure that you understand what authors mean by the different terms like action or action type or operator, etc. So in PDDL, this action has the unique name move that can be used to identify this action, this operator. And it has several parameters that are defined here. And there's one parameter, which is this one, a variable. Remember, variables start with the question mark, R, which is of type robot. And then it has 2 more variables, both of the type location. This is what we've called the name of the operator in the definition of a strips planning operator 2 slides ago. Next, we have the preconditions and effects. So the preconditions are introduced by the precondition symbol and then are just listed. It is also explicitly stated in PDDL that this is a conjunction of preconditions, so they all must hold, and that's what we introduce with the AND symbol. PDDL actually also allows other preconditions, disjunctive preconditions, but we will not look at those here. So what we have is that the first precondition is that the 2 locations must be adjacent, the robot must be at the first of those 2 locations where it's starting from, and this location must not be occupied. Slightly different syntax, but exactly the 3 preconditions we've seen in the previous slide. Similarly, for the effects, they're listed here. They are a conjunction of effects, and it's the same 4 effects we've seen previously, namely that the robot must be at the 2 location, as a result of the action, and this location will be occupied. The robot is no longer at the from location, which is no longer occupied. You should now be able to express the other two operators introduced in the previous slide in the PDDL notation. So why don't you do that as a little exercise here?